In the proton NMR spectrum, we can find what we call cluster of peaks. So a group of small peaks banded together in a particular position. The position of that cluster of peaks will tell us what type of hydrogen we are looking at. A hydrogen attached to a carbonyl group, a hydrogen in a methyl group, a hydrogen attached to an oxygen with a single bond. The cluster, the number of peaks that are huddled together will tell us information about the neighbors, the neighboring carbons, what happens to the hydrogens in adjacent carbons. How do we call the clusters? Well, we have only one peak in our cluster, we call that a singlet, 2 peaks a doublet, 3 peaks a triplet, and 4 peaks a quartet. And typically, if you find more, you call them multiplets. So singlets, doubles, triples, triplets, quartets, and multiplets. So what do those clusters tell us about the structure of our compound? Well, the number of peaks in a cluster tell us how many hydrogens are in the adjacent carbons. So not in the carbon in which that hydrogen is attached to, but the adjacent ones. So when we have a singlet, one peak only, that says that in the neighboring carbon there is no hydrogens. If our peak is a doublet, that means that in the neighboring carbon is a carbon that has 1 hydrogen. So the hydrogen we are looking at in that particular position is next to a CH group. If we see a triplet, then the hydrogen is next to a carbon that has 2 hydrogens, so it's next to a CH2 group, or is in between 2 carbons, and those 2 carbons have 1 hydrogen each. And finally, if we have, for example, a quartet, then typically what it means is that the neighboring carbon has 3 hydrogens. It's a methyl group. Or it could also be that there are 3 neighboring carbons are surrounded that carbon attached to the hydrogen, and each of them has 1 hydrogen. Let's have a look at this NMR spectrum and see how it illustrates the splitting in an NMR spectrum. So if I draw here the structure of our compound with the CH2, and this carbon that has only 1 hydrogen is attached to 2 bromines. So first, let's look at this hydrogen here. And let's look at how many hydrogens are in the neighboring carbon. So there is no neighboring carbon on this side. There's only 1 neighboring carbon here, this one. And that neighboring carbon has 2 hydrogens. That means that the signal corresponding to that hydrogen is going to be a triplet. It has 2 neighbors, n equals 2, plus 1, 3. That's what we call it the n plus 1 rule. So this signal here, around 5.5, it's though it cannot be seen very clearly, you can see it better in the expansion, it's a triplet. And that is a triplet associated with this hydrogen that in the neighboring carbon that has 2 hydrogens, that is near a carbon, next to a carbon that has 2 hydrogens. 2 plus 1, 3, and that's where the triplet comes from. Now let's look at these 2 hydrogens. So these 2 hydrogens are together. They will appear in they are chemically equivalent. They will appear in a particular place in the NMR spectrum, the proton NMR spectrum, and they will give a peak. What will be the splitting of that peak? Well, for that we need to look at the neighboring carbon. So in the neighboring carbon there's only 1 hydrogen. That carbon has only 1 hydrogen. So n in this case equals 1, 1 plus 1, 2. Those hydrogens will appear as a doublet, and it's actually this peak here. And they appear as a doublet not because there are two hydrogens. They appear as a doublet because in the neighboring carbon, that neighboring carbon has only one hydrogen, and that's what gives the doublet. So the position of the peak, the fact that it's at 4 ppm or 5 ppm or 6 ppm, tells us what type of hydrogen it is, whether it's near a bromide, near an oxygen, near a carbonyl group, forming part of a benzene ring, etc. The position tells us what sort of type of hydrogen we are looking at. The splitting of the peak tells us information about the hydrogens in the neighboring carbons. So we not only have information about that particular hydrogen, but the ones in the adjacent carbons. Let's continue looking to the splitting of the peaks, what we call spin splitting. Remember, the position of the peak tells you about that hydrogen or set of hydrogens that are chemical equivalent. The splitting tells us information about the hydrogens in neighboring carbons. So if we look at this compound, we can see that there are two types of hydrogens that are chemically non-equivalent. One of them is what is called in the spectrum HA. They are the hydrogens of the methyl groups, and they're identical because they're chemically they are bonded to the same atoms, and they are identical. They will respond in the same way to the NMR spectrometer. They will give the same signal. As far as the NMR spectrometer is concerned, they are identical. They are the same type of hydrogens. So they will appear in a particular place in the NMR spectrum. What will be the splitting of that peak? Well, for that we need to look at the neighboring carbon. And this is the neighboring carbon. And the neighboring carbon has only one hydrogen. So 1 plus 1 equals 2, and n plus 1 rule. Those hydrogens will appear as a doublet. A very big doublet, this one here. Very big because it represents 6 hydrogens. There are totally 6 hydrogens in that environment. And a doublet because those hydrogens have, as in the neighboring carbon, one hydrogen attached. Let's now look at the other hydrogen non-chemically equivalent in this molecule, and that is Hb. So again, because it's a particular hydrogen in a particular environment surrounded by assorted atoms, it will appear in a particular part of the spectrum. What will be the splitting of that peak? Well, for that we need to look at the neighboring carbons and the hydrogens that are attached to those neighboring carbons. So in this case, this hydrogen, this hydrogen has 2 neighboring carbons, one on each side, and they are both methyl groups. In total, there are 6 hydrogens, 3 on each side So the n plus 1 rule would tell us that what we're expecting to see is a multiplet with 7 peaks, and here it is. A multiplet with 7 peaks that correspond to those hydrogens, what in the slide is called Hb. You not always are able to see the very large multiplets very clearly. They can sometimes be a bit narrow and crowded, but in this case, expanding the spectrum show us the 7 peaks that you would expect, because that hydrogen has 6 hydrogens in neighboring carbons, 3 on each side.